started. I've distributed exams to all of you who are here, both of you who are here, I should say. And so there are a couple of things that I want you to do with regard to these exams. The first thing that I would like for you to do is to take a look at the multiple choice questions. And I want you to divide them up into 3 piles. I want you to divide them up into questions that you did not understand. In other words, language problems. I want you to divide them up into questions that you did understand but did not know how to do. Multiple choice.
Oh.
So actually get those questions out at this time. You remember I gave you your packet back yesterday. Did not know how to do. And the third pile is ones that you did know how to do, but you made silly mistakes. Let's call it execution problems. And if you're listening at home, I want you to pull out your multiple choice and do that at this time also. Divide the questions up into those 3 categories. And then having identified those 3 categories, then I'd like for us to get an emotive discussion started on these multiple choice questions so that we can be really, really clear about everything. You guys did well on the free response. The multiple choice were weaker than I wanted. And so I would like for you to put some time and effort into really debriefing these and dividing it into these 3 piles right here. You might want to write these categories down so that you know what you're looking for. Okay, and welcome back. I would like now to focus on the free response questions, just a couple of small points that were very commonly missed on the free response questions. Generally, you guys did really well with these. I think all of you improved your scores with the free response, and so I was very pleased, but there were just a couple of things that I needed to talk about. In the first problem, you were told that g of x is equal to the integral from 2 to x of f of t dt, and at one point you're asked to evaluate g of 0. Now I do need to say a word about labeling. Some of you jump straight into a computation without labeling what you're doing. Kenneth Clark, I'm talking to you. I want you to label everything. You know that. So make sure that you do some labeling. So g of 0 should be the integral from 2 to 0 of f of t dt. And all of you got that. Now there were 2 things that had to happen in order for you to execute well. One is to recognize that 0 is less than 2. So I really need to reverse these limits of integration like this to get the opposite of the integral from 0 to 2 of f of t dt. And then the second thing was that in integrating from 0 to 2 f of t dt, I'm looking at this area right here, right there, and I need to just visually observe that that area is going to be negative. And when I multiply that by -1, I should get a positive value. So my intuition should be set before I jump into calculating. Now as I calculate it, I'm going to treat that as a triangle, so it's 1/2 based on its height. And here we come to the second issue. Some of you tried to calculate this by counting squares. Do not do that. Use the scale. The distance here is 2, not 4. And the height here is taken as -1 because it is sine height. And that -1 here times this -1 here is what gives me my positive value of +1 for g of 0. I had a number of students give me either -1 or even I got -4 as one answer for this because people counted squares instead of using the scale to determine the thing. Okay? So that was that. The first problem was worth 2 points. Yes, 1 for each value. Moving on to our second question. The sketching of graph of G, I do want to talk about, but not today.
Oh, so are we like going over some few problems?
Yes, exactly. Yep.
So when do we have time for the like our information?
I want you to put those questions out on Edmodo so
Um,
that we can have a good class discussion about them. So we have an implicitly defined curve, blah, blah, blah. You guys had defined dy dx. I think all of you did that accurately. That should be x squared y prime plus 2xy plus 2xy y prime plus y squared equals 0, so that y prime in is equal to negative 2xy plus y squared over 2xy plus x squared. And that was actually worth 3 points. Find the equation of the tangent line. Use point slope.
I
It's not doing y equals mx plus b.
what does that mean?
Here.
So I use the linear.
Right. You use y equals mx plus b. Stop doing that. Use point slope. Y minus y1
Oh,
equals
okay.
slope times x
But
minus
is
x.
isn't it gonna be keep me the same?
Of course it will.
Yeah.
But this is easy to use here.
Oh.
And that's not.
Okay.
Right.
Yeah, like this is like I'm really used to it, so it's really hard to change.
I'll just walk through this. I think all of you computed correctly that the slope was negative 8/5, and so you get y minus 2 equals negative 8/5 times x minus 1 as your tangent line.
Oh.
Right there. Okay. Now I asked you to use your tangent line to estimate a value of y when x equals 0.9. Many of you worked too hard on this question. All that you needed to tell me was that y is equal to 2 plus negative or minus 8/5 times 0.9 minus 1. That is a number. Stop there. I had some people take and simplify this incorrectly and lose credit on a perfectly good answer. Stop. Tell your inner nerd to shut up at this point. Okay. Then the big story was to find the points where the curve has a horizontal tangent. So let's move down and consider that.
So we have like so many values for
No, actually, there's only one. Yep. So we have already dy dx equals the opposite of
x squared plus 2.
Yep. And in order for the tangent to be horizontal, that requires that the slope be 0. Now, here is where a number of you showed some algebraic weakness. And I want to make sure that we are thinking clearly and strongly about this. Point 1. If a fraction is 0, its numerator must be 0. So I can set immediately y squared plus 2xy equal to 0. Point number 2. Factoring is your friend. I should automatically solve this by factoring if I can, and I can. And this gives me two solutions, y is 0 and y equals negative 2x. Right. Now, y equals 0 might give me a point. Y equals negative 2x is definitely not a point. So I'm definitely not done here. So the third point, if I have an equation that has two variables, then what do I need? Wrong thought. I need another equation. If I've got two variables, I need two equations that are independent of each other. Yes! Yes! I know something about x and y. I know that x squared y plus y squared x is equal to 2.
Now we substitute.
Absolutely. And so when I substitute y equals 0 in here, doesn't work, can't have a point. So this solution we reject. And when I substitute y equals negative 2x into here, correctly. Then I get x squared times negative 2x plus negative 2x squared, quantity squared, x is equal to 2, which simplifies to negative 2x cubed plus 4x cubed is equal to 2, or 2x cubed is equal to 2, or x is equal to 1. Nice and convenient, almost like I set it up that way. And once I know that x is equal to 1, I immediately know that y is equal to negative 2 times 1, which is negative 2. And that gives me my single point of horizontal tangency, which is 1 comma negative 2. So the three thoughts that we needed to have are, first of all, fraction 0 means numerator is 0. Second thought, factoring is your friend. And third thought, two variables, two equations.
So I don't know where I was.
I did not understand how you got from here to here.
Oh, I do.
Oh,
Yeah, I just like.
all right. Okay. When that happens, do something so that I can see that. It's not obvious to me that this could be any right? So you need to communicate it clearly. I will give you a point on that, but in the future I want you to make very clear where your work is. Okay. On the third question. The third question was interesting because it kind of pushed your algebra a little bit. So I asked you, for example, at what time does he return to the factory? And so the thought is that if he's going to return to the factory, then his displacement must be 0. And his displacement is the integral of the velocity. And it's going to be equal to the integral from 0 to t of the velocity, which was root t times 4 minus t dt. And so a lot of you set this up, but then when it came to the executing, it became problematic. So this gives me, when I do the actual integration, I end up with 8/3 t to the 3/2 minus 2/5 t to the 5/2 is equal to 0. And so now the question is, how am I going to solve? What do you think I'm going to tell you?
So I divided by t.
Do not divide. What is your friend? Factoring is your friend. Solve it by factoring. And we notice that we have a common factor of t to the 3/2 here. And when I factor out that t to the 3/2, lo and behold, I get 8/3 in the first term minus 2/5 of t to the 2/2 equals 0. And this gives me two solutions. T equals 0. That's why you don't divide, because you accidentally divided by 0. Boom. And the second solution is when 8/3 is equal to 2/5 t, or in other words, t is equal to 40/6, which is 20/3, just like that. Easy solution, but only if you are committed to factoring as a method of solution. Right? Total distance, not too bad. The key here was to recognize when he turns around. And he turns around, we already did that, at t equals 4. So our total distance will be the integral from 0 to t v of t, where velocity is positive. And then I'm going to integrate from 4 to 9, the opposite of v of t, when the velocity is negative. And then carry on from there.
I thought the total distance means that just displacement.
No. Total distance and displacement are different, and the picture you want to have in your mind is if an object starts, let's say the object starts here at 2, and he goes to 5, and then comes back, then his displacement is delta s. No, it is actually negative 2. And it doesn't matter how he got there. But the distance.
Oh, so distance we count all the. Oh, okay.
Yeah. Yep. So notice that delta S is the integral of the velocity, because that integral gives me the net signed area under the curve, and net signed area is going to count negative velocities as negative displacement, right? Backwards direction, whereas distance is going to be the integral from A to B of the speed. Here it is.
So what's this one?
How many points was it? Just 3 total. So you had to set up the right integral, and then you had to actually get to the other. Okay. And so those are the major things that I saw in the free response questions. You may have some other questions, and you'll put those out on Edmodo, and we'll get a good discussion going. For the remainder of our time, what I'd like to talk to you about today, and what I will also be talking to you about on Monday via video, is 2 ways to estimate integrals using shapes other than rectangles.
Oh, before you go, can I say your point that you go
This is distance here. Yes. So this is equal to the integral of the speed from 0 to 9. And to integrate that speed, I integrate from 0 to 4 velocity when velocity is positive. And then I integrate from 4 to 9 the opposite of velocity when velocity is negative. Good. Okay. So let's change gears here. And our goal is efficient estimation of integrals. And the reason this is a problem for us is that what we would like to be able to do is to compute these integrals with as few computations as possible, because we are imagining that we are writing computer code that is going to compute these integrals, and if that computer code runs slowly, it's going to annoy the heck out of everybody. So we want our computer code to run as quickly as possible, and so for that reason, we want to take as few steps as possible, as few additions and as few multiplication operations as possible. And when I talk about efficient, that means as few steps as possible, but also we want accurate estimates, meaning that our error is small. And when you take those 2 characteristics and combine them together, we have to be clever. I can be really efficient. I can estimate an integral with just 1 subtraction and 1 multiplication. If you ask me to integrate from 0 to pi sine x dx, then I can say, hey, look, sine goes from 0 to 1, pi, and so my estimate is going to be 1 times pi. Ta-da! Efficient, but not very accurate. In fact, really what this is an upper sum, right? It is the worst possible upper sum. So this is, in some sense, the worst possible estimate that I can do is a horribly inaccurate estimate of the actual answer, which is 2. It's got an error of 1.414, sorry, 1.14159, blah, blah, blah. Okay, so our story so far has been a story of left sums, right sums, midpoint sums, okay, upper sums and lower sums. And so what we would like to do is to choose some better shapes. And our first shape is going to be a trapezoid. Trapezoidal method. So that if I have a curve y equals f of x, and I wish to integrate from a to b, then rather than covering my curve with rectangles, I'm going to cover my curve in sort of partition scheme here with trapezoids. So that I'm going to connect from here to here, and like that, and like that, and like that, just like that. And you can visually see that the trapezoids do a really good job of covering this area. So that I expect that my error will be small, even using a small number of trapezoids. Hey, accurate and efficient. That's exactly what we were aiming for here. If you compare that to five rectangles, you can see that these two rectangles would be pretty good, but by the time I get to a rectangle over here, unless I choose the point just at the right place, then I'm not going to do it. So, the only question then is, first of all, what is the area of a trapezoid? And then, how do I generalize that to summing up the trapezoids? And then, what can I say about the error that I have in my approximation? So let's answer those questions, and that'll be a good day's work. So the area of a trapezoid, if I've got a trapezoid like so, then I'm going to estimate the area by taking the average height right here and multiplying it by the width. See? So the area of the trapezoid should be average height. But because the trapezoid has a straight line cut across right there, this triangle and this triangle have exactly the same area, which means that my average height is simply equal to the numeric mean of the first and last of the two bases right there. And so the area of the trapezoid, if we characterize this in terms of function values, is going to be equal to f of x sub I plus f of x sub I minus 1 all over 2 times delta xi. Does that make sense to everybody? And so now it's just a matter of summing it all up. My trapezoidal estimation, which I'm going to call T, we're going to use the symbol T for the trapezoidal estimation, is going to be the sum from I equals 1 to n of the average of each two heights times delta x. In other words, I'm going to walk down trapezoids 1, 2, 3, 4, and 5, and I'm going to take average of heights, average of heights, average of heights, all of that, just like that. And my smartboarding accidentally made it seem like it was a midpoint sum, which is not. So please notice that the trapezoidal sum is not the midpoint sum. The midpoint sum is a sum of rectangles whose heights are chosen at the midpoint of each interval. The trapezoidal sum is the sum of trapezoids, whatever the average height is. But if I unroll this sum, I notice something really interesting about this, and that is that this is equal to this guy right here, right? Just doing the algebra on this. And this is, right here, a right-hand sum. And this is, right here, a left-hand sum. So that the trapezoidal sum can also be thought of as the left-hand sum plus the right-hand sum over 2, or the average of left and right sums. And this is a common way of computing the trapezoidal method if you happen to know left and right-hand sums. I want to show how this works out in two particular cases. First of all, I want to show you how it works out in terms of data, how we go about doing trapezoidal sums with data. And second of all, I want to show you how it works out in the special case where we have equal width partitions, because that's a very common case. So let's do that. imagine that I've got some velocity data, and I want to estimate the integral of velocity, which will give me,
The acceleration space.
I displaced the 0, maybe 1, 2, 3. I skipped one, and then I skipped a couple more. My timer got lazy on me, and it didn't record all the values, so I ended up with this guy. And so my velocity is going to be, let's say it's 5, 6, 8, 4, 1, and 0. And I'd like an estimate now for the displacement. And so the way that I'm going to do that is to operate in much the same way that I did for left and right sums. The only difference is how I'm going to handle my heights here. I'm going to compute the delta t's. Yeah, and then for my heights, I'm going to take average height for each one. 5.5 is my average height here, 7 is my average height here, 6 and 2.5 and 0.5 is my average height there. And now my trapezoidal sum, I would notate it like this. The integral from 0 to 8 of v of t dt is approximately equal to, and now I'm just going to walk through and do average height times dt times delta t for each one. And it's really that simple. And if my inner nerd feels compelled to simplify it, I can, but I don't really feel like I want to do that at this time. Does that make sense to everybody? So that's handling data. It's really pretty easy. We just have a Riemann, we have a partition of our interval from 0 to 8, and then we are going to add up average heights there. I almost said something wrong. It's not a Riemann sum that we're doing. Why is it not a Riemann sum? Because I am not actually picking one particular f value for any point in the curve there. As it turns out, if my curve is continuous, then it has to go through each one of these values. So it is a Riemann sum of sorts, but I'm actually not guaranteed that my curve necessarily is continuous to do the trapezoidal estimating. Okay? All right. The next question is, what happens if my partition is equally spaced? So that my delta x is equal to p minus a over e. In that case, we get some nice simplifications popping out of this, and I want to talk about those simplifications. So we'll start with our trapezoidal formula here. But now, because my partition is equally spaced, this delta xi right here is a constant b minus a over n. So I can now pull the b minus a over n and the factor of 2 all to the outside, like that. Like so. So that's a little bit of a simplification, because if we're thinking in terms of computation here, what I have done is to greatly reduce the number of multiplies that I have to do. Right? Because previously I was going to have to do fxi plus fxi minus 1, and then do a multiplication here, and then do a multiplication there. Now I was able to pull all that out, and all I have to do is add up these guys. But wait, there's more. Because if we take this sum and we unroll it a little bit, then you can see that when I is equal to 1, what I get is f of x0 plus f of x1. That's for I equals 1. For I equals 2, I'm going to add on to that. Let me group this like this. For I equals 2, I'm going to add on fx2 plus fx1. For I equals 3, I'm going to add on fx3 plus fx2. Plus, all the way down the line, the last one that I add on is fxn plus fxn minus 1. Now, if we're thinking in terms of efficiency, computer scientists always light up when they see something that they've already computed. Notice that when I compute f of x1 here, all I have to do is remember it there. I don't have to go compute it again. And in fact, how many of these do I have? Well, I have one here and one there. I have 2, really, right? And I also have 2 of these. And I have 2 of f of x3s. And I have 2 of everything on down the line, except for the first one and the last one. That's exactly right. Now let's visualize this so we can see it really clearly. What we're saying is that if this is my function from A to B, then because I am averaging left and right, then what that means is that I'm going to take the average of these two. Yes, I'm going to take the average of these two. I'm going to take the average of these two. I use all the middle ones twice and the outside ones one time only. So that when I simplify that to our final result, what I get is b minus a over 2n times f of a, which is also f of x0, plus 2 fx1s, plus 2 fx2s, plus on down the line 2 fxn minus 1s, plus 1 of the last one. What's fascinating about this is that we're thinking of this really as a kind of weighted average here, where all of the inside ones count twice as much as the outside ones. The outside ones only count once, and all the ones on the inside count twice for the average. And the fxn, of course, down here is 10 degrees. Does that make sense to everybody? Okay. Well, how are we doing with our questions? Do we know how to compute the trapezoidal sum? Yes. Can we visualize it pretty well? I think so. All right. So the only question then is, we've managed to make it as efficient as possible. The only question now is, how accurate is the trapezoidal sum? Visually, we see that the trapezoidal sum appears to be much more accurate than a rectangular sum of any sort, unless my rectangles are sort of perfectly chosen. But it's definitely more accurate than a left or right sum, for sure. So the question then is, how accurate is it? And for that, I'm going to do a little bit of hand waving. I'm just going to present you with a result, but I'm going to provide you with a document that gives a proof of the result. Okay? To get the actual error, we do the usual. We're going to compute the difference between our trapezoidal sum and the actual integral.
Is there an error bar?
What's that?
Error.
Is that an error bar?
Error bound.
Error bound. Oh yes, that's where we're headed with this. This is the real error. Unfortunately, this real error is unknown to us unless I happen to know the exact value of the integral to begin with, in which case, why am I wasting my time with a trapezoidal approximation, right? So, generally speaking, this is going to be unknown.
You mean the exact value?
The exact value of the error is unknown. If I knew it, then I would just take my trapezoidal sum, I'd add on the error, and I'd have the integral. And I wouldn't need to worry about this.
So it's just,
It's a theoretical, right? But I can say something about the error. I can say that the error, let's call the error epsilon. I can say that the error is going to be bounded from above. It's bounded from below by 0, right? Because it's the absolute value of the quantity. Right? The error is going to be bounded above by this quantity right here. B minus A cubed over 12 in the square.
isn't this all going to be a
Mm-hmm. Times the maximum of the absolute value of f double prime over the interval a to b. And the book calls this ET. I don't like this notation because it conveys the idea that this is the actual error. It's not. It is an upper bound on how bad the error is. I'll give a quick example of using it. But before I do that, I want to observe the factors that make this error bound larger or smaller. So we have a large error bound, not a large error necessarily, but a large error bound if n is small. That is, if I'm only using a few trapezoids. That makes sense. Or if b minus a is wide. In other words, if I'm integrating over a large interval, then I'm going to be less accurate for a given number of trapezoids than if I'm integrating over a small interval. Or if the max of f double prime is large. Now, what does it mean for the max of f double prime to be large? Well, it basically means that my function has a severe concavity issue.
why is f double prime?
Why is that involved? Yeah, the proof will take care of that. That will explain that. But intuitively, I want to show you that it makes sense. Let's take a curve that has very small concavity. Hey, it's a straight line. When I integrate that with a trapezoid, look at that. I actually get perfection. Let's take a different curve that's really curvy. And now let's estimate the area under this curve with a single trapezoid. Look at all that error that I missed. All that area that I accidentally over-included. And I over-included it because my curve deviated in a large way from the straight line that it cut across.
This one has f double prime.
And exactly so. This one has a large f double
Oh,
prime.
so it's making the largest error they can make.
Yes.
Oh.
Exactly.
Okay.
Yes. Very good. Okay. So we have a large f double prime right here, and that will cause this thing. By the way, we can also say something a little bit more. Notice that f double prime is positive here, curve is concave up, and as a result, the trapezoidal sum is too large because it cuts across the top of a concave up curve. If by contrast my curve were concave down, then a single trapezoid would cut across the bottom and it would underestimate, it would leave out some area. So we can actually say something not only about the size of the error, but also about the direction. If f double prime is positive for all x on a to b, then the epsilon will be no, we better say it like this. That means the trapezoid is an overestimate. And if f double prime is negative, then the trapezoid underestimates. Very quickly, let me do an example. I'm going to estimate that the integral from 0 to 2 of x squared dx with two trapezoids. Now, we already know the answer to this. We can do it in our heads. X cubed over 3 from 0 to 2 is 8/3. There's our real answer. Okay. Pretend we don't know fundamental theorem. If I'm going to estimate with two trapezoids, then I'm going to say that this should be equal to b minus a over 2n times f of x0 plus 2 times f of x1 plus f of x2, just like that. And here's my trapezoidal estimate. And we label it right there. And that gives me 1/2 of 0 squared plus 2 times 1 squared plus 2 squared, which is going to give me 6 over 2, which is going to give me 3. Yes, we observed that the trapezoidal sum is an overestimate. Why? Because my curve is concave up. So actually what we did was this and this, right? And it's an overestimate. All right, so we know it's greater than the integral. By how much? Let's put a bound on this. We know that the error is going to be less than or equal to b minus a over 12 cubed over 12n squared times the maximum of f double prime. And that's going to be 2 cubed over 12 times 2 squared times the maximum of, hey, since f is x squared, f double prime is 2. And maximum value of 2 is 2. And so that's going to give me, let's see here, 4 over 12, which is 1/3. So my error is no worse than 1/3. Okay, now is this the actual error? No, it's not. It's just a bound on the error. Let's see what the actual error is. It may be, let's see here. 3 was our thing, 8/3 was the integral, and that turned out to be 1/3. So it turned out that in this particular case, our error was equal to the error bound, but that is not always the case. The error bound is